Snowflakes carry entire atmospheric stories inside their shapes. Every delicate branch, every sudden angle, every pattern that looks like it was intentionally designed is the product of something that happened in the sky for a fraction of a second. When you watch snow drift down, from a distance it looks calm and simple, but each individual snowflake is a record of motion, temperature, pressure, and humidity. Most people will go their entire lives without ever seeing one up close. When people come to my page or view my art, they come with curiosity. Some come for the science, some come for the art, some come because they saw a short video online and wanted to know if what they saw was real. Some come because they want to understand the natural world in a way that feels gentle and hopeful instead of heavy or frightening. And some come because they have been told that snowflake preservation is impossible or fake or too strange to believe. So I created a space where the focus can shift to something good, something rooted in science and wonder without bias or fear. In this long exploration, I wanted to take time with you to explain everything, not in a rush, not oversimplified, and not in a quick little 1-minute sketch. I wanted to explore what a snowflake actually is down to its physical makeup. I want to explain how much of a snowflake is air, how little water it contains, why its structure forms the way it does, and what happens when I preserve it. I want to show the details of the reaction, why the polymer works, why certain crystals fail, and why the tiniest environmental shift can change everything. I want to explore the history that came before me, the earlier scientists and photographers who documented these crystals. I also want to talk about my own beginnings, how I came into this work, why it is meaningful to me, and how I continue to open new doors. I also want to widen the lens. Snowflakes are only the beginning. They teach us how to pay attention. Once you learn to see something as delicate as a single ice crystal, you begin to notice the quiet phenomena happening everywhere. The way water forms patterns in mud, the way ice grows in branches on windows, the way light arcs through the sky in ways that seem impossible. We spend so much of life rushing past things that are actually remarkable. I want this channel to be a place that slows people down, a place that gives a breath, a place that lets wonder return without trying to frame everything as controversy or disaster, not to ignore the real world, but to balance it. Before we go anywhere else, we begin with the snowflake itself, because the truth is, most of what people believe about snowflakes is not accurate. From their shape, to their weight, to their structure, to their water content, to how they behave when they land. Almost all of it is misunderstood. Most people think a snowflake is a little solid piece of frozen water, something dense, something cold, something like a miniature bead of ice. But a snowflake is nothing like that. A snowflake is an open lattice made mostly of air. That is not an exaggeration. Atmospheric scientists have measured the density of snow crystals for over a century. Wilson Bentley, the first known photographer of snowflakes, studied the mass in the late 1800s by collecting them on chilled metal plates. Modern researchers like Kenneth Lebritt at Caltech have studied them through advanced microscopy, laser imaging, and controlled laboratory growth. Their findings agree. The average dendritic snowflake contains between 90 and 95% air by volume. Some extremely thin crystals approach 97% air. The intricate branches that look solid in photographs are actually thin sheets, only a few micrometers thick. They are so delicate that even slight warmth can change them before the reaction begins. They are so airy that wind can destroy them without leaving a trace. This is why holding one barehanded, it melts instantly. You're not melting a thick object, you are destroying a fragile architecture made of tiny threads of ice surrounded mostly by empty space. If you compare a snowflake to something familiar, the scale becomes even clearer. A single raindrop holds about 0.05 grams of water. A large snowflake holds about 0.0004 grams of water. That is 4 millionths of a gram. So what is a snowflake really? It begins with a nucleus. This is a tiny particle in the atmosphere. Dust, pollen, mineral, ash. Water vapor molecules attach to that nucleus and freeze into a hexagonal pattern. The six-sided symmetry is the foundation of nearly every snowflake, but the shape it becomes depends entirely on the environment. Temperature affects the thickness of its plates, humidity affects the growth rate of its branches, and pressure affects the formation of its side ridges. The air changes while the flake is falling, and the crystal shape will change with it. This is why a single snowflake can look like it was grown in different styles as it passed through layers of the atmosphere. Some snowflakes form long needles, some form simple hexagonal plates, some form capped columns that look like tiny spools. Some form dendrites with sweeping branches, some form extremely rare shapes like triangles or 12-sided plates, and these shapes form within narrow windows of conditions. This is why certain types are rare. The atmosphere has to be just right in just the right moment. Now, we move to preservation, the part everyone wants to understand, the part that seems impossible until you learn how it works. People hear the word resin and picture thick, glossy mixtures used in craft projects. That is not what I use. In chemistry, the word resin is broad. It refers to any substance that begins as a liquid and cures into a solid. Tree sap is a resin, varnish is a resin, many paints are resins, many plastics begin as resins. The polymer used to preserve snowflakes belongs to that scientific category, but it behaves nothing like craft resin. The polymer I use is thin, reactive, and designed to interact with frozen surfaces. When it meets the surface of the snowflake, it triggers a fast reaction. That reaction forms a micro-thin film that seals the structure. The word seal here matters because once the film forms, the ice inside cannot melt, cannot drip, and cannot shift phases. It is no longer exposed to air movement or temperature changes. The ice becomes immobilized inside the sealed structure. What remains is the true architecture of the snowflake. People often misunderstand this part. They think the ice disappears or melts or evaporates or gets replaced. That is not how this works. Once sealed, the structure cannot undergo phase change. It cannot melt because the environment needed for melting no longer exists. It instead remains in the exact arrangement it held in the sky. And this is why calling the result a replica is inaccurate. Nothing is recreated, nothing is molded. The geometry you see is the true geometry of the snowflake that fell from the sky. Tryggvi Emilsson first documented this reaction process in the 1970s. His work showed that a thin polymer could stabilize the structure of an ice crystal long enough for it to be studied. His work provided the first clear understanding of how snowflakes could be preserved in their true arrangement. Many preservation methods used today are variations of that foundational concept. My own method uses a combination of known science and technique. I have developed personally. Some parts I do keep private, not to guard or gatekeep, but because every craft has a heart, and that heart belongs to the artist who nurtured it. A large part of understanding snowflake preservation is understanding failure. I think most people imagine you might preserve 50, maybe 20, maybe at least 10, but the reality is very different. The success rate for delicate dendrites can be under 5%. On difficult days, closer to 1%. The majority collapse before the reaction can seal them. They bend, melt at microscopic points, fracture or distort. Sometimes they break apart before they even land on the tray. Snowflakes are structures built from thin walls of ice that are barely there at all. This means that preservation is not simply an artistic choice. It is a constant partnership with environmental conditions. The cold must be stable, the humidity must be right, the tools must be chilled, the reaction must be quick and precise. There are no shortcuts and no guarantee. The outcome is shaped by factors you cannot always see. When I talk about the process online or when people visit my gallery, they often ask why a preserved snowflake costs what they do. They imagine the cost is for the water or the resin or the setting material, but the value is actually in the rarity, the time, the failures, the technique, and the environment required to protect something so incredibly fragile. A preserved snowflake is not only the story of everything that happened before it, the storm forecasts that had to be right, the late nights, the freezing hands, the careful captures, the attempts that failed, the one moment where everything aligned for that snowflake to carry on. Snowflake teach patience, and patience meets patience without conflict. My daughters grow up seeing their mother work with something delicate and fleeting. They see me choose gentleness over force. They see me fail more often than I succeed and still continue. They see me treat the tiniest things with respect, and I hope that stays with them. They may never choose this craft or this career, and that I will understand, but I do hope that they care and pay attention and create meaning behind the small things. My own beginning with snowflakes was not scientific, it was emotional. I tried to save a snowflake from my daughter's first snowfall. I pressed it gently on a cold surface and felt the ache of watching it vanish. The small moment sparked a fascination. I had seen snow all my life growing up in Colorado, but I had never closely studied the snowflakes. That night I began reading everything I could find about snow crystals. I found photographs from Wilson Bentley, the man who spent his life capturing these shapes under magnification, long before the public even knew such intricate forms existed. His dedication was inspiring. He worked quietly, alone, in the cold, with no fame during his lifetime, only devotion to showing the world something beautiful. Later, I discovered the work of Tryggvi Emilsson, whose scientific research opened the door to snowflake preservation. His research showed that a thin polymer film could hold the architecture of the ice in place, allowing it to exist far beyond the moment of snowfall. I do not think he ever imagined an artist would use his findings to create jewelry or snowflake display pieces, but his work is what made this all possible. I always return to these two figures because they represent both sides of this craft. Bentley represents the wonder, and Emilsson represents the science. Both matter, and without Bentley, people might not ever have cared about snowflakes. And without Emilsson, the preservation process might never have existed at all. I am not the only person doing this work. There are a few snowflake preservation artists around the world, each with their own approach. Each method has strengths and challenges. Each finished piece reflects the hands that made it. I believe there is room for everyone in this field because the sky delivers endless variations. No one will ever capture the same snowflake. No one will ever create the same piece. Snowflake preservation is a rare practice, but not a competition. It is a dialogue with nature. Now that we've covered the foundation of structure, water content, and preservation chemistry, we can explore the atmosphere itself. Because understanding snowflakes means understanding the environment that forms them. A snowflake begins in the clouds, but its formation depends on narrow bands of temperature. At around freezing, water vapor tends to form simple hexagonal plates. A little colder and needles form. Colder still and dendrites begin to branch. Humidity also matters. Higher humidity leads to more complex structures. Lower humidity leads to simple ones. This is why some storms produce large, intricate flakes and others produce tiny sand grains. The atmosphere is layered like a slow-moving ocean. A snowflake falling through it experiences changing conditions. A crystal might begin as a simple plate, then drift into colder air and grow branches, and then fall into warmer air and grow smooth ridges. The final structure carries this history. It is a timeline in ice. This variation explains the existence of rare forms. Triangular snowflakes form when one side grows faster than the others due to subtle shifts in airflow. 12-sided crystals form when plate growth stabilizes. And pay attention. The more time you spend studying the sky, the better you become at predicting what will fall. I read weather maps the way some people read novels. I watch the temperature, observe patterns of storms. I look at the humidity changes before and after cloud layers shift. With enough practice, you can tell which storms will bring needles and which will bring plates and which will bring branching dendrites. You cannot predict everything, but you can certainly learn to read the tendencies and to read the storm. Diving into something deeper, we want to talk about snowflakes, and snowflakes being the entry point to this channel, but they are not. The destination is wonder. The destination is awareness. The destination is learning to see the world without rushing past it. There is a way of living that comes from noticing small things. It helps you feel grounded. It helps you slow down when life feels overwhelming. It helps you stay connected to nature when everything around you seems chaotic. I want this channel to be a place where people can feel that. Not through fantasy or escapism, but through seeing real natural phenomena with clear eyes. For example, most people have seen frost on a window, but have never studied the patterns. Frost grows in branching lines called rime. It forms when water vapor in the air freezes onto a cold surface. But the shapes it grows can mimic ferns, leaves, feathers, and trees. Ice does not simply freeze, it organizes, it branches, it expresses the conditions around. Another example is hoarfrost, a form of ice that grows outward from cold surface in delicate spikes. Hoarfrost forms when air is saturated with moisture and it touches a surface that is below freezing. The ice grows outward like white coral. Some formations look like crystal forests, some look like feathers, some look like fragile sculptures shaped by breath. Then we have diamond dust. This is one of the rarest forms of precipitation. Diamond dust is made from tiny floating ice crystals that glitter in the sunlight. It usually forms on extremely cold, clear days. People who live in milder climates may never see it, but once you have seen diamond dust, you understand how alive and complex the winter atmosphere truly is. There are more phenomena: sundogs that appear as bright spots on either side of the sun, ice halos that circle the sun or moon, light pillars that rise vertically in the sky. Each of these effects comes from the interaction of light with ice crystals in the air. Snowflakes are not only important for their shape, they are part of a larger system that creates beauty in the sky every single day. Which brings me to the subject of water. Is one of the most unusual substances in the natural world. It behaves differently almost every... This brings me to the subject of water is one of the most unusual substances in the natural world. It behaves differently from almost every other material. It expands when it freezes. It can dissolve more substances than any other liquid. Its molecules form hydrogen bonds that create complex structures. The study of water connects chemistry, physics, weather, biology, and geology. Snowflakes are only one expression of what water can do. I want this channel to explore the deeper story of water, the way rivers carve landscapes, the way lakes freeze from the top downward instead of the bottom upward, the way supercooled water can remain liquid below freezing until disturbed, the way ice crystals form in clouds around tiny particles. Water is gentle, but it also is powerful and complex, and it deserves attention. This long-form video is not only about snowflakes, it is about learning to see nature in a new way, to see patterns where you once saw blankness, to see detail where you once saw simplicity, to understand that the world is layered with phenomena that are happening whether or not we notice them. So let's continue our journey and go into a deeper study of... The deeper you go into the study of snowflakes and water, the more you begin to notice a larger truth. Nature is not chaotic. It is patterned. It is responsive. It reacts to everything around it in ways that can be seen if you slow down. A snowflake is not random. A weather pattern is not random. The shape of frost on a window is not random. All of these forms are messages from the environment. They are records, scripts written in the cold. When most people step outside during snowfall, they see the whole scene. They look at the storm as one event, but the atmosphere is writing millions of tiny individual stories at the same time. No two snowflakes are the same, not because of magic or myth, but because no two paths through the atmosphere are identical. Every snowflake experiences unique conditions as it falls. That is why every preserved snowflake carries its own signature. Many viewers wonder why some snowflakes appear more detailed than others. Some storms produce large branching dendrites with obvious complexity. Others produce tiny grains that almost look like dusts. The difference comes down to air temperature and humidity. At temperatures just below freezing, snowflakes grow as simple plates. As the temperature drops, their growth becomes more complex. Dendrites form most easily around 14 degrees Fahrenheit, when there is also high humidity. This is why the most beautiful crystals often appear during calm, cold snowfall without strong winds. The presence of wind can distort a crystal. Winds push snowflakes into each other, and they break branches. They cause collisions that leave marks, and many snowflakes that fall during windy storms never become perfect dendrites. They arrive broken, chipped, or incomplete, and this is why capture conditions matter. Calm air leads to better snow crystals. When people ask why their snowflakes at home look simple, the answer is often humidity. Low humidity produces simple shapes. High humidity produces complexity. The atmosphere is always shifting, but once you learn the signs, you can begin to anticipate the type of snow that will fall. Understanding these patterns helps you see that snowflakes are not decorations from nature. They are meteorological artifacts. They are atmospheric fingerprints that tell the story of the storm that created them. Now I want to shift into another layer of understanding. The way people perceive nature, the way beauty intersects with science, and the way curiosity shapes perception. Most people grow up hearing science presented as a list of facts, a series of rules, and something rigid, something separate from emotion. But science is not separate from wonder. Science is the study of wonder. It is the study of how beauty forms, how patterns arise, and how complexity appears out of simple ingredients. The more you learn, the more astonishing the world becomes. I started to create these longer form explorations to remind people that the world is not empty. It is layered with meaning. There are details all around us that go unnoticed because life moves too quickly. Snowflakes become a medium for slowing down. Some of the most meaningful messages I receive are from people who say they had forgotten what wonder felt like. People who say that seeing a preserved snowflake reminded them that there are still things worth pausing for. This is why I talk about natural phenomena. The world can feel heavy, but when you look closely, it is also full of gentle miracles. Returning back to science, many viewers want to understand the actual mechanism of the polymer reaction I use. While I protect the specific details of my personal method, I can explain the general scientific principles behind snowflake preservation. The polymer must be reactive at low temperature. When it touches the frozen surface, the snowflake initiates a quick bonding process. That bonding forms a thin film. The purpose of the film is to freeze the geometry in place. Once the film forms, the ice inside can no longer exchange heat with the environment. The microstructure becomes secured. The environment required for phase change no longer exists. People sometimes imagine the ice turning into gas and leaving the structure, but that is not how sealed reactions behave. Once sealed, the architecture is held in place and protected from external conditions. The snowflake turns solid, and this can be done with common household items such as superglue, lacquer, a few hairsprays. This is where the term replica becomes confusing. In scientific literature, replica can refer to any structure that remains after the original material is no longer active. But in everyday language, replica means or implies fake or copied. What remains in a preserved snowflake is the true structure, it is the real geometry. The word replica simply does not describe what I create. People also misunderstand the word resin. They imagine thick mixtures used in craft projects, but the polymer I use is nothing like that. Craft resin is heavy, warm, and slow to cure. It would destroy a snowflake immediately. The polymer used in snowflake preservation is thin, fast-acting, and chemically compatible with frozen water. It creates a protective film, not a dome or a cast. If you want to try simple experiments at home, the easiest method is to use a chilled surface, Place a piece of aluminum or glass outside until it matches the outdoor temperature and catch snowflakes on it and observe them under magnification, or you can lightly mist them with clear acrylic spray from a distance to create little imprints. This will not preserve the fine structure and it will not create anything close to a true preserved snowflake, but it does allow you to explore the shape safely. Caltech provides instructions for classroom experiments using FormVar, which can give better results. Everything I do builds on these foundations, capturing crystals, protecting their structure, and presenting them in a way that lets others see what would have been lost. But I want to expand this channel into new areas as well. There is so much to explore. Atmospheric optics is one of my favorite areas of study. These are the interactions between light and the ice crystals. In the atmosphere, sundogs, for example, are plate-shaped ice crystals aligned horizontally. Ice halos form when light bends through hexagonal crystals. Some contain rare features like tangent arcs or circumcenthal arcs that look like upside-down rainbows. Most people see these effects without understanding what creates them. Once you know how ice crystals interact with light, the sky becomes a storybook. You can look at a halo and tell what shape of crystal is forming it. You can look at a sundog and understand the orientation of the ice in the atmosphere. The same is true of light pillars. These are vertical beams that rise into the sky when light reflects off falling ice crystals. They look supernatural, but they are simply the result of crystals catching and reflecting light in the right alignment. All of these phenomena connect back to snowflakes. They are formed by the same types of ice crystals, just in different environments. Snowflakes fall to the ground. Atmospheric crystals remain suspended in air, but both are shaped by cold, humidity, and motion. Now, I want to talk about something broader, the idea of wonder without bias. The idea of learning without fear, the idea of seeking understanding without jumping to conclusions. We live in a time where information spreads quickly, but understanding spreads slowly. People see a video of a preserved snowflake and are quick to claim that it is fake. Not because they understand the science, but because they have not been shown that it is possible. They hear the word resin and assume plastic. They hear the word preservation and assume replica. They hear that the ice does not melt and assume impossibility. But the natural world is full of processes that seem impossible until you understand the conditions. Think about amber. Think about fossils. Think about ice cores. Think about crystals growing in caves for centuries. Preservation is not a strange idea. Nature does it constantly. What I do is a human-guided version of something nature has always been capable of. Stabilizing structure and protecting beauty, holding form. But the purpose of this conversation, this channel, is not to convince anyone of anything. It is to offer accurate information, clear explanations, and a space for people to wonder. People can decide what they believe. I simply offer what I know, what I have seen with my own little eyes, and what I have learned through years of dedication. Everything I create is done in freezing conditions. My tools stay cold, my surfaces stay cold, my hands, because it is not only scientific, it is not only artistic, it is a philosophy of attention. When you work with snowflakes, you are constantly reminded of how temporary everything is. You cannot force a snowflake to form. You cannot control the weather. You cannot predict which snowflake will survive. You can only show up, observe, and respond. This teaches humility, and it teaches presence, and it teaches a kind of acceptance. Snowflakes are small teachers. They remind you that beauty often lasts only seconds unless you choose to notice it. They remind you that delicate things have value, and they remind you that life does not need to be loud to be meaningful. This channel is a way of sharing that, a place where people can remember how to pay attention, a place where science and art meets, a place where learning is soft instead of sharp. As we move into the last part of this long exploration, I want to widen the lens even further. Snowflakes brought many people here. Their shapes, their rarity, their mystery, their impossible looking geometry. But this channel is meant to grow into something larger, something that moves through water, weather, atmosphere, geology, and all the quiet natural phenomena that unfold around us every day. Things that go unseen not because they are invisible, but because life moves too fast to notice them. We live in a world where attention is constantly pulled towards noise, towards conflict, towards fear. It is easy to forget that beauty exists at the same time. That good things are not gone. They are simply quiet. They do not demand attention. They wait for someone to look closely. Snowflakes are my doorway to the quiet world. They taught me to slow down. They taught me to observe details that cannot be rushed. They taught me the value of patience and the importance of responding to conditions rather than resisting them. And now they help me teach others how to see that too. As this channel grows, I want it to become a place of unbiased learning, a place where facts are clear, never harsh, a place without judgment, a place where natural phenomena can be presented as they are. Out agenda. A place that shows people how to find real wonder again. Let us return to the science of snowflakes one more time before moving outward, because repetition, when done in a deeper form, builds understanding. A snowflake is mostly air, 90 to 95%. Some snowflakes, particularly thin plates, approach 97% air. This means the water content is incredibly small. 4 millionths of a gram is not enough to measure with consumer tools. It is barely enough to register on laboratory instruments without careful calibration. When the public learns this, it often surprises them. People imagine snow as frozen rain, but the structure is nothing like a droplet. Rain is dense. Snow is empty space held together by fragile architecture. This is why the structure collapses so easily. This is why preservation is so difficult. The structure must be sealed instantly. If it is not sealed, it will change. The smallest amount of warmth can soften a branch. A small airflow can break an edge. Even the breath from your nose can distort the structure. The polymer creates protection before any of these changes can occur. Once sealed, the ice can no longer melt or shift. People often try to imagine what happens to the ice afterwards, but the reality is better question what does not happen. The ice does not melt because the environment for melting is gone. The ice does not evaporate because it is not exposed to air. The architecture is preserved and the structure remains. The geometry of the original snowflake stays completely intact. That is the heart of preservation for me. Not replacing the snowflake, not copying the snowflake, not creating a fake, but protecting the original snowflake so it can remain as it is. This is why the call-outs of fake or replica absolutely misunderstand the process. They imagine what they already know about resin and assume it applies here, and it does not. Now, let us take this understanding and expand into water science. Water is one of the most unusual and important substances on Earth. Nearly everything about it is strange, and everything about it affects life. Water expands when it freezes. Most substances contract when they freeze, but water, it expands. This is why ice floats, and if ice sank, oceans would freeze from the bottom upward, creating a frozen world where life could not thrive or live. Water's expansion protects life. Water dissolves more substances than any other liquid. This ability makes it essential for chemical reaction in the atmosphere, for weathering of rocks, for soil formation, and for nutrient movement inside living cells. Water can remain liquid below freezing when undisturbed. This is known as supercooled water. It becomes common in clouds. When supercooled droplets encounter a nucleus, they freeze instantly. This is the start of snowflake formation. Water molecules create hydrogen bonds, which are temporary but powerful. These bonds create the lattice structure that allows snowflakes to grow in precise geometric ways. Without hydrogen bonding, snow would not form patterns at all. It would be more like glass shards or dust. Water is the quiet architect for almost everything around us. Snowflakes are simply one of the most delicate expressions. Now, moving into a broader philosophical space, When you work closely with phenomena like snowflakes, you begin to sense a deeper rhythm in nature. Not a mystical rhythm, but a scientific one that feels just as profound. Patterns repeat across scales. The branching of a snowflake resembles the branching of a river delta. The hexagonal structure of ice reflects the hexagonal patterns in basalt columns. The way frost grows on a window resembles the way crystals form in rocks. Nature reuses patterns. This is not a coincidence. This is mathematics, expressed through physics. It is the same reason tree branches and lightning bolts look similar. Both follow the path of least resistance. Snowflakes follow this same principle. Water vapor attaches where the structure can grow most easily, creating branching patterns that match larger patterns found everywhere in nature. Once you learn to see these repeating structures, the world becomes far more interesting. This channel will eventually explore those connections, how snowflake geometry relates to fractals, how branching patterns appear in biology, geology, and weather, how symmetry arises naturally, how order appears in systems that seem chaotic. People often ask why I do this work. Why snowflakes? Why something that requires long nights, cold conditions, and so many failed attempts? My answer is that this work reflects life. It teaches presence, it teaches care, it teaches patience. It teaches you that you cannot force conditions. You can only work with what is given. It teaches that small things matter. And it teaches that beauty can come from quiet places. I am a stay-at-home mother of 2 children. I homeschool. I manage a home. I run a business. My days are full, and my nights often involve stepping into the cold to capture crystals. But this work gives meaning to the rhythm of my life. It allows me to show my daughters what patience looks like. It allows me to teach them how to notice the small things. And it shows them that their mother built something from absolutely nothing, and something made from patience and cold and quiet dedication. People tell me often that what I do is unusual, but I think the world needs unusual things, especially now, because unusual things remind us that the world is larger than we realize. They remind us that there is more to see, more to learn, and more to appreciate. So that's the direction of this channel, to explore unusual things, natural things, beautiful things that do not ask for attention, but definitely deserve it. Snowflakes are the beginning, but we will explore frost, ice halos, supercooled water, atmospheric optics, rare weather events, mineral formations, water science, and other natural phenomena that weave together the story of our planet. Now I want to speak directly to the people who support my work. Your comments, your encouragement, your curiosity, and your kindness have allowed me to grow faster than I have ever expected. I am one person, and there are so many days when I cannot respond to every message and every comment, but I see them, and I am so grateful and appreciative of you. If you want to reach me directly, the best place is through my website. Social media messages often get buried, and email is far more reliable for me. As for new work, the snowflakes I have recently captured will not be ready until January. I am currently preparing a page to begin giveaways of older pieces. Custom orders are currently closed and will not start up again until after the new year. You can absolutely email me if you'd like to be on a wait list for first captures. In the months ahead, I will upload weekly videos, long-form explorations like this one, close-up footage of snowflakes, educational content about water and weather, stories from science and nature. Snowflakes were my beginning. They are a reminder that even the smallest things hold complexity and meaning. They are a reminder that the world is full of quiet wonders waiting to be seen. They are a reminder that beauty can exist even in the coldest conditions. Thank you for spending time with me. Thank you for your curiosity, and thank you for your openness and for being here. Thank you for choosing to explore something with me today.